I welcome you all to this first of the seminars in our Reproducibility Showcase series that MIDAS is running this summer. I'm Jagadish, Director of the Michigan Institute for Data Science. At MIDAS, we've been thinking about reproducibility in research, broadly speaking, with, of course, data being a central part of that. And we thought we'd begin by just understanding the strength and diversity of work that we have already ongoing at the University of Michigan, find a few strong examples that others could learn from, and use that as a starting point both to improve how the rest of us pursue our respective research projects to try to make them more reproducible, and also to identify shared interests, possible joint research avenues for the future, etc. We had planned to have a reproducibility day to celebrate the work of so many of our colleagues in April, but because of the COVID-19 related closure, that has been postponed to some future date. We're hoping September, but whenever it becomes feasible to do. Meanwhile, we had so many really, really wonderful examples of work that our colleagues had done and are doing that the world, and certainly all of us at Michigan, should hear about and try to emulate and learn from. And so we thought we'd put this showcase series together. And today is the very first of these talks. It is by Johann Gagnon-Bartsch from the Department of Statistics. And we're going to do this showcase series as a moderated conversation rather than as a formal lecture. And we had a committee of colleagues who helped figure out the projects that we are featuring in this showcase and evaluated the work of our colleagues in choosing good exemplars of reproducibility. And one of those committee members, Arvind Rao, is here with us today and will be the moderator. And with that, I'm going to turn this over to Johann and Arvind.
Thanks, Jag. Thank you so much. So again, welcome, Johann. Wonderful to have you do our first kickoff talk in this series. I've just let the audience know that Johann's submission scored unanimously well. Everybody loved the tone of the way he articulated the whole challenge around reproducibility, replicability, but also the solutions that he offered. So constructive and so practical. I think there was unanimity in the group's consensus that this was really a wonderful way to showcase reproducibility. So, Johann, before we get into your presentation, I had a couple of quick questions for you, if I may.
Okay, thank you, Arvind.
First of all, basically, could you tell us a little bit about your background, your interests, and your specific take on the reproducibility crisis and your own philosophy about what ingredients need to be part of that? How to address the reproducibility challenge that's become so endemic to the way science is currently being done.
Yeah, so a little bit of background. I'm an assistant professor in the statistics department. My research interests are fairly diverse, but all pretty applied. So I work with social science data and high throughput biological data for the most part. I'll be talking about a couple different projects that I've worked on today. And so, yeah, you'll get a sense of that, and also how I've handled reproducibility as far as they go. As to your question about how I handle reproducibility and how I think it can be handled, one of the things that I'll try to emphasize when I give my talk today is that for most, what I'll call everyday cases, it's maybe not actually that much extra work to ensure that your analysis is fully reproducible. So I guess I view the challenge of reproducibility as pretty solvable, at least in most cases. There's a different challenge of replicability. Just to be clear, when I talk about reproducibility, I talk about, I mean just like literally being able to, on the computer, with the same data, get the same results as what shows up in a paper. And I think that that's pretty doable, and I'm going to try and talk about various tools that people can use to do it. Replicability, so basically having one researcher get the same sorts of results using different data, their own analysis. That's quite a bit harder, and I don't know that there's an easy answer to that, but at least towards the end of my talk, I'm going to say a few words about things that we can do as data scientists that can help. With the answer mainly being to do a lot of what you could call sensitivity analyses, or just basically checking how robust your results are to small changes in your analysis.
That sounds fantastic. So with that as the preamble, I think we're all very eager to hear your presentation. So I'll just quickly mention the title that Johann gave us. Is basically Everyday Reproducibility, a multi-pronged approach to ensure analyses are fully reproducible, easy to access, and easy to use. And in that vein, I have to once again tell you all that the solutions that Johann offered as part of the challenge were definitely scoring very high on all these axes. So with that, I invite Johann to give his presentation. Thank you.
Thank you very much, Arvind. And I'd also like to thank everybody who helped organize this reproducibility challenge. I think it's a wonderful idea. Okay, so hopefully I have my screen shared now. Yes. As Arvind said, my talk is Everyday Reproducibility, Multi-pronged Approach to ensure analyses are fully reproducible, easy to access, and easy to use. So brief outline, I'm going to spend a few minutes talking about goals of reproducibility. And then I'm going to just talk through 3 projects that I've worked on where I tried to make the analyses as reproducible as possible. And this will have somewhat of a narrative in tone. It's 3 projects in chronological order that I worked on, and kind of what I learned along the way. And then and these are the 3 projects that I submitted to the reproducibility challenge. And then after that, assuming I have time, I'm going to try and talk just a little bit about, well, beyond just straight up reproducibility, other challenges. Okay, so starting off just by talking about some reproducibility goals, here are a few. The first would be that you want the entirety of the analysis to be fully reproducible. So you want to be able to start with the data and then get to the exact same results that you have in your paper. So the exact same plots, exact same numerical results. So that's one goal. In doing that, though, you might also want your code to be easy to access, inspect, and understand. So it's one thing to have your analysis be fully reproducible, but part of the reason that you want it to be fully reproducible is so that people can fully understand what you did, or at least understand what you did to the extent that they need to. And so for that, you need your code to also be easy to look at, easy to access, easy to understand. And you also would ideally like your code to be reasonably portable so that other people can use it, and so that it can be useful to other researchers. And so I guess the first point that I want to make is that these are distinct goals, and each of them might be best served by a different tool. And so in what I talk about, I'm going to emphasize the use of Docker for making sure that the entirety of the analysis is fully reproducible. And I will talk about what Docker is. I think that GitHub is a pretty good solution for making code especially easy to access and inspect. You don't even need to download it. You can just look on the web and see the code. And then CRAN or other package management systems. CRAN is a package management system for the R language, as a way to package up and make sure that the core routines or any code that you think is especially modular and can be used by other people in the future as a way of distributing that nice and easily. There's other goals in reproducibility, of course. Those are just the few that I want to spend the most time talking about. But just to list a couple others, just as you want your code to be easy to access, inspect, and understand, and also to be portable and useful to researchers, you can say the same with the data. You'd like the data to be as easily as accessible by others as possible, and also processed in a way that they can immediately look at it and use it. For storage of especially large data sets, some good tools for that might be Synapse or GEO or ICPSR. I think most disciplines have a kind of go-to data repository, so it's good to use those. And as far as making data easily accessible, another thing that I'll kind of mention as I go along is that it's good to, in your code, create any intermediate, clearly create any intermediate data sets that are useful. So if you start off with some raw data and then you do a bunch of pre-processing to it, and most of your analyses are done on the pre-processed data, it's good in your code to kind of clearly have a section that does all the pre-processing, saves the intermediate data, and then have additional scripts that carry on from there. And that way other people can come back and they can either look at the raw data if they want, or they can look at your cleaned up data if they want. Another issue is making sure that the analysis is safely archived. So once you've got everything set up and it's all reproducible, you also make sure that it's stored somewhere where the storage is persistent, where it will stay. And another reproducibility goal that one might have is to make sure that all of your code version history is saved. That is, I think on the whole, maybe having the code version history saved on the whole is more useful for the researcher themselves, him or herself. But these tools, and especially GitHub, make it easy to do, and you'll be, or at least I've found that you'll be thankful if you do that. Okay, and a final comment before I move on. I'm going to be focusing on what I call everyday reproducibility, meaning reproducibility that I think most people can do in most situations. So I'm not going to be on especially challenging aspects of reproducibility, such as when, for legal reasons, you can't share your data or anything like that. I'm going to focus on situations where the code that you write is something that you can share, no proprietary code. You can share your data. The data isn't astronomically large. So that's what I mean by everyday reproducibility. So with all that said, like I said, I'm going to talk about just 3 projects that I've worked on and kind of talk about this in a narrative sort of way. The 3 projects, the first is a project that I did for balance testing and observational studies. One on cell type estimation that I worked on with a PhD student, Greg Hunt, and then also a cell image analysis project that I also worked on with Greg. I'll start with the balance testing project. This is, like I said, it's a balance test for assessing covariate imbalance in observational studies. There's a paper if you're interested. I'm not going to talk a whole lot about the method itself, just to give you the flavor of the type of research project this is, and then I'll talk a little bit about kind of what was in the paper, what analyses I did, and how I went about making them reproducible. So I'll take maybe a minute and a half just to talk about the research project itself, just again so that you've got a basic flavor of what happened in this project. So it's a test for covariate imbalance, and it's meant to be used in observational studies where for example, maybe a natural experiment or regression discontinuity design or matching design, where the researcher has done something to try and ensure that two groups are comparable and in some sense approximate a randomized experiment. Okay. The way I first got into this project was with my collaborator Johann. Johann read this paper here by Lyall and found that he didn't fully believe aspects of it. So the paper that Johann read was looking at whether or not indiscriminate violence might incite insurgent attacks. So what this study did was it compared bombed villages in Chechnya and then looked to see whether the bombed villages gave rise to more insurgent attacks. And as part of the analysis, the researcher matched on covariates of the villages. So in the paper, there was a balance table like this. You see balance tables like this in the social sciences quite a bit, where they kind of go through various covariates, such as the populations of the villages, and show that between the bombed and the unbombed groups, the covariates are roughly the same. So they roughly line up in terms of population, in terms of their poverty level, and so on. And here's p-values for each of these. And then the typical argument is that because they line up in terms of their covariates, the two groups are roughly comparable, and so it makes sense to do some sort of causal analysis on them. Johann was skeptical. In particular, he thought that even though each of these covariates looked balanced in the marginal distribution, perhaps they were imbalanced in the joint distribution. So we talked about how we could go about looking into that. And this is a method that we came up with, which we call the classification permutation test. And the basic idea is we train a classifier to distinguish the treated from the control units. And then the idea is that if we can actually perform that classification successfully, which we measure by looking at the classification accuracy rate, then you can't really make a good argument that the treatment and control are essentially as good as random. And to make the inference valid, we get our p-value by permutation test. Okay, so again, that's just to give you a flavor of the type of project this was. Rather, I want to say straightforward kind of statistical method project. Oh, and there, by the way, is the results. There's the null distribution of the accuracy rate, and then here is the test statistic for the Lyall data. And so in fact, we see that it's actually quite imbalanced in the joint distribution. Anyway, so what's in the paper? We have several simulations, and then we have four data examples. This Chechnya example that I just went through, and then a few other examples. Each of these examples has kind of their own storyline. We're showing and talking about different things in each of these examples. So these are, I want to say, 4 distinct analyses in addition to the simulations. Okay, so when submitting the paper, we decided that we wanted to make sure that it was fully reproducible, just because we felt that that would be a good thing to do. And here's what we did to do that. First, we created an R package for the method. So we feel that the method itself that we're talking about is generally useful. So we made an R package for it, and we put it onto CRAN so that other people could access it. And then all of our other analyses from there on out used that R package itself, just so that, you know, when we make claims in the paper about this method doing that, there's a very clear instantiation of the method that people can refer to. Okay, we also made an R package for data and helper routines. This is not an R package that we put on CRAN, that just ended up on GitHub, but it's helpful partly in case anybody else wants to come reanalyze the data. Having it all in an R package makes it very easy. None of these data sets are very large. And then having various helper routines, also in case any future researchers kind of want to take our analysis as a starting point and go from there. And then we had some scripts to run the analyses. And we basically wrote this as one script per analysis, just to make it nice and clear what does what. And then we said we just throw everything on GitHub. Okay, and that seemed pretty good. Okay, so then time passes. A few months go by, and then it's time to revise the paper. And when revising the paper, so we updated our code a little bit, reran a couple of the analyses, and well, we see that we got very different results for one of the methods that we had been comparing against, a different balance test. So that was kind of disturbing. And so we did a great deal of debugging to try and figure out what had happened. And I should say at this point, I was not very committed to anything like Git and having a good versioning of my code. So I had to kind of do my best to just kind of go back and look to make sure when I had last edited my code, and is the plot that we had in the paper really from the most recent code and all that. And eventually figured out that, yeah, it wasn't anything that we had changed or had done wrong. But I finally remembered that in the previous couple of months, I had updated my my R package library, and then by kind of looking through all the dependencies and whatnot, realized that a dependency of a dependency of a dependency had changed in a way that actually changed the results. So This all took several weeks to figure out and was quite a pain. So the moral of all of this is that saving your code is not necessarily enough. And you need to save your entire computational environment. That sounds like a lot of work. I'll hopefully convince you that it's not. And in the long run, given these kinds of debugging issues that you might run into, in the long run, it really does save you time. And the solution to this, at least the one that we use and that I find very good, is Docker. So I'll talk about Docker here for a few minutes. So Docker is a virtualization software, containerization software. What it does is it allows you to neatly package your entire analysis within a virtual environment. And in particular, everything, the operating system, all the software, all the libraries, all the packages, and so on, all of this is saved within the Docker image. And then once you've created this image, it can be run on any computer that has Docker installed. And so it can be a Windows computer, Mac, Linux, whatever. This Docker image, since it's a virtualized environment, it can be run on any computer that has Docker. And the image can also be hosted on Docker Hub, which makes it easily accessible by anyone. So here, for example, is the Docker Hub page for my classification permutation test analysis. So if you just go to this URL, this is the web page that you'll get, and it gives a few instructions on what to do. And so if you look right here, for example, if you have Docker installed on your computer, and I should point out it's free and easy to install. If you have Docker installed, then all you have to do is open a terminal on your computer and type this line right here. And what will happen is the image will automatically get downloaded and will get run, and the entire analysis that is in the paper will get run on your computer. It'll take a couple days, but the entire analysis will get run, and then all of the plots and all of the output will appear. So that's quite nice. So to reproduce the analysis, all someone has to do is type this one line of code, and the entire analysis will get reproduced. There's just a couple of other options here of things you can do. For example, if you just want to extract all of the code and the data that's in the image, you can type that. So the Docker makes it very, very easy for someone to reproduce the analysis. Now, that might sound like a lot of work, but what I want to emphasize is that it's really not, and it's certainly worth it. So how do you do this actually? So you want to start with some well-organized code that runs your entire analysis, and I recommend before putting together a Docker image, have your code already nicely organized on GitHub. And then that way you can basically build a Docker image that runs exactly what you already have on GitHub. So that way you're not kind of reinventing the wheel. You already make sure you already have your analysis kind of nice and tidy in one spot, and then just at that point, essentially you just want to Dockerize it. So here's the analysis for this paper on GitHub. There's a README that tells you what you need to do to run the analysis, and in particular which R packages you need to install. And here are the two R packages that we created that I mentioned. This one actually is also on CRAN, and then this is the one that contains the data and helper routines. And then there's all of the individual scripts inside that replication directory. If you look inside that replication directory, it's, like I said, very simple. It's just one R script for each of the different analyses that occurs in the paper. Each one of these is, say, 100 lines of code or so kind of nice and easy to follow. Okay. So you've got some nice code ready to go. Then all you have to do is put your code into a directory and create what's called a Docker file, a file called Docker file. And that's just a text file that you use to configure the Docker image. Again, that might sound like it's going to be kind of involved, but actually it's pretty straightforward, and there's typically not a whole lot to do, mainly for the reason that there are already many pre-configured Docker images out there that you can build upon. So for example, here is the entire Docker file. It's just 24 lines for this particular analysis. So this first line here from our base, that is to start with a pre-configured image that's already available that has R installed on it. So just by typing this from our base, you get to start with an entire virtualized environment that already has R installed. It's a Linux Ubuntu environment has R installed. And then you've got these add commands, and they add files to your Docker image. So for example, I've got this directory called Docker files where I've got a couple extra files that I added. They'll show up below. This replication directory, that's directly from GitHub. That's those scripts. And then I also add the Docker file itself, just so that anybody can inspect it if they want. All this command says is where you're going to run the commands below. You've got a couple commands here to make the scripts executable. So you do need to have at least a very basic working knowledge of say, Linux or Mac command line, but again, very minimal. These couple lines install a couple extra libraries that are needed. Knowing what libraries to install can also be a little bit of a challenge at first, but basically what happens is if you try to install an R package within the environment and you get some sort of error, it'll say something like, you need the SSL library, and then you Google for a couple seconds how to install the SSL library in Ubuntu, and you figure out that you need to write that. Okay, and then there's a script that installs the R packages that are used. That literally is just this quick script that installs those particular packages. And then this installs the two packages that I created. And then the very last thing is what commands should get run within the environment when the image starts. Okay, so that's it. After you've created that Docker file, you can then build the Docker image with just a couple quick lines. So here, this first line says to build it and call it CPT. And then the second line, you push it to Docker Hub, and that's it. You're done. So that's all that you actually have to do to make this containerization. And then once you have that, you don't need to worry about, for example, any libraries getting changed on you and all of your code breaking after 3 months. So it's very well worth it. Okay, so going back and thinking about some of these reproducibility goals I mentioned at the beginning, here I've got what I call a multi-pronged approach. We use the Docker to ensure complete reproducibility, GitHub to make the code easy to access and to inspect. Like I said, all you need is a web browser to look at the code. And then again, the R packages and the CRAN package manager to make the actual methods easy to use. Okay. Project number 2. This is with my grad student or former grad student Greg, and we wrote a paper on cell type estimation. I won't go a whole lot into the details here, but basically the idea is, tissues are composed of multiple cell types, and people researchers want to know proportions of different cell types. So for example, how many neurons or astrocytes are in this sample, or how many T cells versus B cells. There's a lot of methods to do this, over 60 the last time I looked. We introduced a method of our own, basically to address an overlooked problem, which is that in most of the existing methods, the combination of data pre-processing that's used, and then the regression models that get used after the pre-processing, the way these are combined result in methods that are, or models that are biologically implausible. So we wanted to fix that. And then here's, for example, an image from the paper where we applied our method to a real data set. Here we've got the true proportion of cells of different types, which is known by fact sorting. And then here we've got the estimated proportion. Where the green, we do fairly well, and these are two other competing methods. Okay, so again, not necessarily to go a whole lot into the method itself, just to give a flavor of what kind of project this is. So what was in this paper? Well, again, we had several simulations. We also had some exploratory data analyses, and then we also did some rather extensive benchmarking analyses. We pulled together 11 different data sets from different papers that have looked at cell type estimation. And for each of these 11 data sets, we applied 9 different existing cell type estimation methods. And then we also had a final application to a Lyme disease data set. Okay, so I asked Greg to take a look at to use my classification permutation test paper as a template, and see if he could kind of do a similar thing for this paper. And for Greg as well, turned out to be very easy. It's something he did in about half a day, I think. So again, we used Docker to ensure complete reproducibility. Greg actually improved on this in a nice way, which is that he introduced various levels of replication. So if you go to his Docker Hub site for detangle, which is the method, you see here he's got kind of 3 different scenarios that you can do. In this one here at the bottom, that will extract all the contents of the Docker image. So that includes all the code, the data, and so on, but also all of the plots that have already been generated, and all the other outputs. So if somebody wants to just kind of download and just look at everything that you have, including the output, they can do that, and that'll happen, more or less instantly. They don't actually have to rerun any code. They can just look at everything. On the other hand, if you do want to rerun the entire analysis from scratch, that command will do that. And also kind of this intermediate option, if you want to take all of the pre-compiled output that we have, so like intermediate data sets, pre-processed data sets and whatnot, and then reproduce just the plots, you can do that as well. So what Greg did here, which I really like and I encourage, is having different entry points, essentially, so that people can reproduce as much or little of the analysis as they want, so they can kind of focus on what they're most interested in. And I should say Greg makes use of the Linux or Unix command make. That's, I think, a nice way to do this. Make has a little bit of a learning curve, but not much. But it's not essential to know make in order to do what Greg did. There's other ways of going about that. Greg also improved the overall reproducibility, I feel, by including a bunch of vignettes and additional examples. And those are found on the GitHub page. And another thing that Greg did, which I encourage, is making a genuine use of Git. So in what I had done in the previous paper, I basically just used Git as a place to post code, let other people download it or look at it. That's that's kind of the most superficial use of GitHub, of course. And if you actually make use of Git and all of the versioning history, you will, well, you'll have all of your code version when you need it. And this is something I also have been doing more and more as time goes on. Git, I want to say, is very well worth learning and using extensively. And then Greg also, as in the previous example, created a package that put on CRAN that implements the core method. And then he also made a data package out of those 11 benchmarking data sets. And this has been very useful, I think, to other researchers. It has made it possible for other people to kind of go and try their own method on the same set of benchmarking examples. So this is, again, kind of in keeping with the theme of when you make your analysis reproducible, that one of the things you want to do is actually make it usable to other people. Having assembled this benchmarking data set, I think is a very nice contribution. Okay, so then here's a third project. Let's see. So this is about cell image analysis. Just looking at the time. Okay, I'll try and talk about this at least a little bit. So this project is a little bit different than the previous two in that the project itself kind of contributes to reproducibility. So I might spend just a little bit more time talking about the project itself and dealing with cell imaging data. So there's new biological assays that make images or take images of millions of individual cells under various conditions. And from those, image features are extracted, things like intensities, morphologies, textures, and so on. And typically, when this is done, there are hundreds of features that are extracted. And kind of importantly, each of these features has their own, in a sense, unique distribution. So some of them are kind of more or less normally distributed, some are skewed, some are highly skewed, some are multimodal, some are counts, and so on. And so you've got all of these hundreds of features, all with their own kind of unique distributions. And then you kind of wonder how do you summarize or integrate all of this information. And so that's kind of what this project is about. We are working specifically with a technology called microenvironment microarrays with some of our collaborators at Oregon Health and Science University who have been working with these rather extensively. So I'll just say you've got wells. Within the wells, you've got a bunch of spots printed, each of which has a different protein in it to change the microenvironment of the cells that are growing on it. And then within each well also, you add different ligands to, again, change the microenvironment of the cells that are growing in there. And so then within a given well, you'll have a whole bunch of different conditions in which the cells are growing. Each spot corresponds to a different condition. If you look at one spot here, you've got several cells growing on it. And so then these cells get imaged and then all these features extracted. And here is just kind of an example of all the different features that you might see. So things about the area and the shape, various intensities, textures, and so on. Lots and lots of features. Again, all of these features have different distributions. Some look more or less normal. Some are highly skewed. These are probably not the best histograms to show, but you get the idea. And so one of the things that we need to do is, just like most basic pre-processing, transform the variables in a way that will make data visualization easier, data integration. I mean, all of these features are on different scales, and we want to have them in some sense on commensurate scales so that we can begin to integrate the information in them, and also to make downstream analyses possible. So we have this, we developed this pipeline, three-step pipeline. The first does a robust Gaussianization of the data. Then we robust z-score and remove anything that is clearly an outlier after all of this. Just to kind of show how this helps with visualization real quickly, here is one feature, CP area shape area, kind of in its raw format, and then after the pipeline, you can distinctly see these two different conditions. So just in terms of data visualization, making histograms and stuff, the transformations help quite a bit. Here's heat maps. These are essentially pseudo images of the wells, heat maps of the features across the well. You can see that if you just make a heat map on the raw data, you don't learn much. Making it on the transform data, you can see things, various technical spatial effects that start to become more apparent. Yeah, I won't, I'm running a little low on time, so I won't go into all of this. Well, here's another nice example of, so before transformations, when you make PC plots, you get kind of weird things that are driven by outliers. Afterwards, here we're able to discover some nice biology, and so on. So that's the basic idea. So again, we did this multi-pronged approach, and for this project too, which is, all of these are, we're looking at fairly, I want to say, heterogeneous set of projects, but all of them seem to be very amenable to this basic approach. Start by making the code nice and easy and organized and clean on GitHub, making a Docker image out of it, and posting to CRAN the core methodology. Again, Greg did this with various tiers of replication, which I think is a very nice idea. And he created vignettes and made good use of Git. And then, like I said, in this particular project, and the reason I spent a little bit more time talking about it, is that I think the project itself contributes nicely to reproducibility in the, at least in the imaging community, because it does all of these transformations in an automatic way. And currently, all of these transformations are kind of chosen manually. So people look at the data and say, oh, this needs to be logged, or this needs to be square rooted, or whatever. This does it all automatically, which kind of removes some, well, what people might occasionally call researcher degrees of freedom. Yeah, so in this case, some of the data was very large, especially the images. So we used Synapse to store and distribute the data. Again, when in situations that, it's nice to have your analysis divided up so that you can create intermediate data sets from the rawest of the raw. Presumably, people will want to use these intermediate data sets. Okay. Just a couple comments on potential improvements, things that I would like to do in the future a little bit better. I think we could do a better job at synchronizing the content between Docker and GitHub. So as it stands, it's kind of like we've got everything in GitHub and then we Dockerize it. But I think it would also be good to have on GitHub, for example, the Docker file and stuff like that, so that anybody can just look at the GitHub and could recreate the Docker image themselves. Then it would serve as a nice template for other people as well. We could also do a better job at archiving the R package versions on GitHub. So inevitably you will update your R package and update it on CRAN. When you do that, it's good to have very clearly marked on GitHub the version that you used for the paper in case it differs in any important way. Another thing is to think about is persistent storage. I don't get the impression that Docker Hub is really intended as a place for images to sit archived for years and years and years. So thinking of different places to store your images for the long term is something that we want to think about. And then also we'd like to create some tutorials and templates to make this very easy to do for anyone who's new to it. Here's some resources, some links. I'm going to, sometime in the near future, try to start putting some templates and tutorials on my GitHub, so please check back soon. Okay, and then I want to spend, I know I'm getting low on time, but I want to spend just a couple minutes here talking about issues that are beyond just straight up reproducibility. So Arvin asked me at the beginning there about my feelings on reproducibility and replicability, and I said that I think that reproducibility is fairly achievable, and I've kind of explained just now why. Well, I want to say that there are other things that we can do as data scientists to improve ultimately replicability, and even just I'll say maybe the credibility of an analysis. So what I'm going to talk about here is not really so much replicability, but what I'll maybe call reproducibility plus. So here's the project. It's involving Twitter data. And here's a brief little bit of background. Basically on social media and public opinion, surveys just in general, like public opinion surveys, those are becoming more and more challenging for researchers to carry out, mainly because non-response is increasingly becoming an issue. And as a result, people are kind of, or at least some people are looking to alternative sources of data to try and gauge public opinion. And one possibility that has generated some excitement is the possibility of using social media data to either supplement or replace traditional surveys of public opinion. And there have been several findings, encouraging findings, such as, for example, that the number of tweets about Obama tracks his presidential approval, or the average sentiment of tweets containing the word jobs tracks unemployment, these sorts of things. But then there's a question of just how real these findings are. Being a little bit opaque by exactly what I mean by real. But here's one example that we looked at in some detail. A paper from 2010 where they find reasonably high correlation between the sentiment of tweets that contain the word jobs and the University of Michigan's Index of Consumer Sentiment, which is a survey. So they looked at this correlation, and they saw a correlation of 0.64, which seems reasonably high. We were interested in this, and what's good is we were actually able to replicate this finding. We didn't have their original collection of tweets. We did not have their code. We were able to get an equivalent collection of tweets from the same time period, subset to tweets that contain the word jobs. And then we wrote our own code to replicate their analysis, and we got a correlation of 0.65, which is, I want to say, shockingly good. We were able to replicate that. Okay, so it wasn't reproducible because we didn't have the original data or code, but we were able to replicate it, which maybe even sounds better. But looking at this even further, so here we kind of can see how just focus on the blue and on the black. The blue is a survey measure of public opinion about the economy. Black is the average sentiment of tweets containing the word jobs. And you see that from around 2008 to 2011, they track each other pretty well. But then if you go further, going up to 2014, all of a sudden they start to not follow each other at all. And so we saw this, and our question was, why did the relationship break down? And so one possibility is just that something important changed as time went on. So maybe the composition of the population of Twitter viewers changed. Maybe the types of tweets about the jobs changed. So for maybe it was like more job advertisements or fewer job advertisements, or maybe more news reports about jobs, or maybe just tweets about Steve Jobs, these sorts of things. Or maybe the style of writing on Twitter changed over the years. So these are the kinds of explanations that are conceivable. Another possibility is that the result was just spurious to begin with. And what's now relevant to all of this, and that we started to look into, is the many analytic factors that went into the original analysis. So in the original analysis, there's involved a sentiment dictionary, which basically says which words are positive, which words have negative connotations, these sorts of things. How you actually end up scoring a tweet using that dictionary, what sort of smoothing you do on the Twitter data, like how many days, how many day average you take to smooth out the sentiment. Lag parameter, you might not, because the surveys are released only every 30 days, you might want to try and come up with some lag between the surveys and the Twitter data. What measure of association you use. So they use correlation, but you could imagine other measures of association. Any pre-processing or filtering of tweets. All of these decisions. It turns out these really matter. Just to give a couple of quick examples, and I know I'm getting really low on time here, but so here's the original 0.65 that we replicated, and this is using exactly the methodology that was in the original paper, and the way that tweets were, or the overall sentiment for a day was scored as the number of positive tweets containing the word jobs for that day divided by the number of negative tweets. So that's one way of scoring the sentiment for the day. Here are some other methods that exist in other papers in the literature. So for example, the number of positive tweets minus negative tweets divided by total tweets, or the number of positive tweets divided by the number of positive tweets plus negative tweets, and so on. All of these on their face seem somewhat reasonable, but you see they end up giving very, very different results. So this 0.65 drops to 0 if we use this scoring method. Bounces back up to 0.48 if we use this one. We also looked at individual subsection or filtering of the tweets, like things that are about news or politics, personal, and so on. I won't go into like the details of kind of what we found about these different ones, but the point remains that the result changes considerably however you score them. Similar thing for what dictionary you use. The original paper used the opinion finder dictionary. Using another one, Lexicoder, or one by Liu Hu, can give different results. It's not as dramatic as a difference from the scoring, but still quite different. As I mentioned, there was a smoothing parameter and a lag parameter. We looked at how that influences things. So they used a smoothing parameter of 30 days and a lag parameter of -50. And that gave this correlation in here about 0.6. But if you look at the space of different lags and smoothing, you find a whole different range of correlations. So this is just to say that all of these seemingly minor decisions can make a huge, huge difference. So this brings me to my point here, which is that when you're making a reproducible analysis, ideally, it should not only be reproducible, but it should be easy for anybody else to go in and explore the impact of all of these analytic choices. That's kind of, in a sense, part of the reason that you want to make it reproducible to begin with, is so that anybody else can take your analysis as a starting point and tweak it, see what is the importance of various aspects of that analysis. Given all of the importance of all of these things, the way that we went about doing this is we created a Shiny app, and you can go to this web page here, and what you'll be able to do is you will see various results for all kinds of combinations of these different decisions. So which you can't see it all here, but you can choose like the sentiment, the way of scoring, the measure of association, all of these things. And using this Shiny app, you can reproduce most of the results that are in the paper, along with many others. So I think that this is something that is highly advantageous to do. Again, this goes beyond reproducibility. This is basically allowing people to reproduce your analysis plus small modifications to it, and checking to see how the modifications change things. But I'll be honest that compared to, for example, making a Docker image, making a Shiny app, that is legitimate work. So this is a fair bit of effort. In this particular paper, the effort was worth it because of the amount of time that we focused in that paper on the importance of small decisions, analytic decisions. But this is, if I'm gonna be honest, is probably not a good option for everyday sorts of papers. You can't expect people to write a Shiny app for every paper that they write. But I think just the broader point here is simply that a lot of these small analytic decisions can make a big difference. And so what I think we can expect of people when they're writing reproducible code is at least to make it, the code clear, to put in some comments along the way of decisions that of where they made specific analytic decisions, and just make the code at least clear enough, readable enough that anybody else that wants to go back in and try tweaking aspects of it, that they're able to. All right, so I'll leave it at that, and thank you very much.
Thank you, Johann. This is really wonderful. Learned so much, and really fantastic scope of work. 3 very different kinds of projects, but all converging on some very nice axes. So thank you again for a fantastic presentation. I think this is a good time to have a couple of questions. I see one already in the chat window, which I guess you can also see, but I'll try to do a good job reading it out. It says from Nicholas N. says, I've done some computer vision analysis. As far as robust Z-score, I wonder if you can say something about that. And he says a little bit more about asking for pointers in the direction of robust testing literature.
Oh, sorry. Let me see if I can. This is in a chat or something.
This is in the Zoom webinar chat on. I guess you should be able to pick it up. He's sent the question to all the panelists, so you might be able to see.
I've done some computer visions as far as robust Z-scores. I wonder if you could talk about that. Oh, so for the robust Z-scores, okay, so I'll say a little bit more about what we did. The first step is to do a robust Gaussianizing transformation. And the basic idea there is you can think of it as a robust Box-Cox transformation. And what made it robust is that, I don't know if you remember, but there are a bunch of different conditions within each well. And these conditions get replicated again and again over the course of different wells, different ligands. And what we did is we did a different Box-Cox transformation for each of these different conditions. And then for the most part, the Box-Cox transformations agreed. But for some, you get something quite a bit different. In some cases, that's just because of artifacts of the data. In other cases, it's because of the biology for one condition ended up being quite a bit different. So what we did is we kind of like took the median transformation, the median Box-Cox parameter. Okay, so after doing that, you get something, the data will typically look more or less normally distributed, but there will be still some, what we refer to in the paper as genuine outliers, things that, you know, it's a segmentation, there's a segmentation error in the image analysis, and so like it includes 2 cells instead of 1 or something like that. And so you get these, what you might think of as legitimate outliers. And so we don't want those to affect the z-score transformations. So, and it's very simple. We just Winsorize the data before calculating the mean and standard deviation. Then get the z-scores, and then we go back and we look for outliers by looking to see if anything after the robust Z transformation has exceptionally large Z-scores. Okay, so that's what we did. Let me finish reading your comment real quick to make sure that I got it. Okay. So Nicholas, I'm not sure if I fully answered what you were asking about, but if you want to follow up with another comment, I can try to respond to it. Arvind, was there anything else that you had to say?
Not really. I mean, you went through all the elements, so it was very helpful. Have you heard any counterpoints about Docker, about its privacy vulnerabilities, and people talking about this other paradigm called Singularity as one more platform for containerized analysis? Do you have any suggestions or thoughts about if somebody was trying to do this today, starting afresh? Based on your background, would you suggest going with Singularity or Docker, or you don't think there's much of a difference? What's your reaction?
Oh, that's a good question, but I can't say that I'm the best person to answer it because I started working with Docker. I found it incredibly easy, and I've stuck with it. So I haven't really looked into anything else at this point. Perhaps I will now that you've asked. But yeah, like I said, I found it so easy, and it takes care of everything that I want to do that I haven't bothered to look at other stuff really.
That makes a lot of sense. And I just bring it up simply because folks that deal with HIPAA constraints around their data talk about some value for Singularity vis-a-vis Docker. But again, this is completely anecdotal and hearsay. I have no first-hand information either. But the fact that you pointed out how straightforward it is to get started with Docker definitely is very helpful. Will help a lot of people. So on that note, I also see one more question in the chat, maybe. Let me make sure I don't miss anything. Yeah, so Nicholas basically writes back saying, I think what suggested is a good place to start, but he could probably contact you offline as well to get more clarity.
Oh yes, that's great.
Yeah, so with that, I mean, I know we have kind of crossed the time limit a little bit, but I can always say that, you know, Johann is so easy to talk to and so good about explaining stuff. I'm sure if folks emailed him with specific questions, they would learn a lot. So if it's all right, maybe we can just call a closure to today's first presentation around Reproducibility Showcase, and we look forward to seeing all of you next time. With that, thank you so much. Thank you again, Johann. And thank you, Jag and Jing, for
I'll echo you just real quick. Yeah, please, anybody that has any questions, please do feel free to get in touch.
Thank you, Johann, and thank you, Arvind. See you all next week.
Bye.